Hello, everyone, and thank you for joining us today for this technical walkthrough of Erigon. We are thrilled to have Mark from the Erigon team co-hosting this session. Mark will walk us through the key functionalities of their code base and share valuable insights into smart contracts and assets. From the Immunify side, I'm Daniel, and I'll be co-hosting the event alongside Mark. So with that, I'll hand it over to you, Mark, to dive into the technical side.
Okay, thank you very much. I'll basically start this presentation with a quick overview of how Erigon hangs together as a set of technical components, and then I intend to walk through the Erigon code base to explain how those key technical elements are implemented. So I'm just going to start presenting my screen. So this presentation is a overview of the components that make up Erigon and how they fit together. So I thought I'd start by talking about the network dependencies, because I think for us, from a general security perspective, Erigon is a very heavily connected. Fundamentally, it's an application that's heavily connected to the network, and it's expecting to operate on an untrusted network, so it's knowingly exposing itself to a whole load of things that it's assuming the blockchain processing will actually resolve, and the software we've got in place can't be exploited. Now, I thought I'd enumerate those dependencies to start off with, explain what they are, and explain which components connect to them. So, at the top of the list is basically the BitTorrent network, and this is because when Erigon starts, essentially the first thing it does is connects to BitTorrent and attempts to download its state of the world. Now, this is slightly different from most other Ethereum clients in that its starting point isn't to connect to the Ethereum P2P network and try and get the state of the world. It has an optimization where it basically connects to BitTorrent to talk to other Erigon nodes and get them to update it with the latest state of the world. Now, the reason we do this is fundamentally for efficiency, because what Erigon has, which I'll explain a little bit later, is a storage model that gives it an efficient, condensed view of the chain, and recovering that over torrents is orders of magnitude faster than doing the same process over the Ethereum network. So the next step in the chain is Erigon, in terms of Ethereum, is a combined consensus layer and execution layer. So it's essentially an all-in-one client. Now, it is possible to run it as without its consensus layer, in which case it will just operate as an execution layer. In theory, we could run Erigon as a consensus layer with a third-party execution layer, but I don't think we've ever tested that, and I wouldn't expect that to work. Now, basically, after the download's completed, the consensus layer piece of the application starts, connects to the beacon chain using libp2p, and essentially tries to establish the state of the world from a beacon chain perspective. Once that's effectively established, Erigon will run its execution layer, which essentially talks to the dev P2P network, which is the kind of older Erigon network, and uses that for maintaining the state of the world. The other component Erigon has that talks to the dev P2P network is its TX pool, or probably what's more commonly known as a mempool. That starts essentially alongside both the consensus layer and the execution layer startup, but actually transaction pool entities aren't processed until the execution layer is caught up. So those layers are effectively the running blockchain application that are receiving blocks, keeping up to the tip of the chain, and processing executions. The final component of Erigon from a client perspective is the RPC layer, which essentially connects via HTTP and services requests from RPC clients for essentially getting read-only access to the contents of Erigon's database using a standard set of Ethereum RPC calls. And it also supports read-write access across the HTTP layer, essentially so you can submit transactions which the node will put into its transaction pool for propagation around the network. The third networking component we have, which we use internally, is gRPC. So essentially, as well as the external network connections that we've got open, Erigon running processes will optionally open a gRPC connection, essentially to allow other pieces of Erigon to talk to it. I'll explain a little bit about how that works in the next slide. So Erigon has essentially two deployment models. They're essentially componentized and combined. The majority use case for Erigon is it runs as a single combined process, and effectively all of the independent components that I've just described operate as essentially separate components, all operating inside of the Erigon process. Now, these processes are internally connected via a direct gRPC connection, so they operate exactly the same way if they're operating inside Erigon or externally. The difference is there's no networking connection in place. If you look at the componentized model, you can see it's possible to run effectively an Erigon execution engine with its internal components connected to separate processes which run the individual components themselves, and essentially they then can be operated as a cluster which effectively provide the same functionality. I think the majority use case of this with Erigon components is essentially running a separate downloader, which means you can run a downloader process that processes the BitTorrent without actually being a full Erigon node, which is useful for sending and receiving snapshot data. Kaplan itself can run as an external process. As I explained earlier, it should run as an external process for applications other than Erigon, and a worthwhile piece of testing may be to verify whether the Erigon consensus layer actually fulfills the requirements of a non-Erigon execution layer, because I think as a development team we've not particularly tested that, because the majority use case we have is running Kaplan as an running our CL as just an internal part of Erigon. Sentry is the name of our P2P connector. I'm not sure where exactly the name comes from, but effectively when it runs in its remote node, what it allows you to do is put the dev P2P process into a DMZ environment. So we're basically protecting the Erigon process from its requirement to have open P2P ports, and that's used by a number of security conscious larger clients of Erigon to protect the core process itself from having such an open network. You can optionally run a transaction pool remotely. The reason for doing that is typically more performance than security, in that the transaction pool is probably the most network intensive part of the application, and it can be beneficial to separate that out from the core process that's trying to keep up with everybody else on the chain. And the final separately run component is the Erigon RPC server. So because Erigon's an archive node, its majority use case is with RPC providers, and depending on the scale that they're operating at, they find it convenient to basically separate the Erigon node that's processing the consensus and the P2P layer from a number of additional nodes that they've got, which are effectively servicing their HTTP clients, which gives them essentially horizontal scalability. Now, the requirements from a performance perspective is you may be running these RPC providers. If you want to run them on separate machines, you need to do this with some kind of optimized shared disk, or else you need to run multiple RPC processes on the same scaled machine as you're running Erigon. And that's because the performance of the RPC daemon is really dependent on sharing the disk and its database with the Erigon instance in order to maintain performance. So these are the ways that Erigon basically runs, and these are the major identifiable components. If we move on a little bit further, what I want to talk about now is essentially Erigon's data layout. Now, the reason for this is because the way Erigon manages data is critical to the way it performs as an application, and it essentially has got its own internal model of the way it keeps its blockchain data. And I'm just describe that now because essentially it will help to understand the overall operations of Erigon. Now, essentially, if we ignore the logs directory, which is just there for logging, the data directory for Erigon is split into two types of data. The first type of data are databases. These basically are MDBX databases that operate independently of each other for certain subcomponents of the system. The most important one of these is the thing called chain data. Now, basically, inside of chain data, you'll find an MDBX couple of data files that give you the tip of the chain data for Erigon. Now, the way Erigon works as a process is it listens to the network connections we saw earlier and runs in a continuous loop with a transaction held open on the chain data store and storing that data. And the way that the transaction and the chain data database operate is pretty dependent for Erigon's overall performance. I'll explain a little bit about the snapshot data in detail in the next slide, but essentially What the snapshots represent is data that's extracted from chain data on a periodic basis and is used then for read-only data. So the reason for this is that basically the chain data growth, I mean, the issue with running chain data as a single MDBX database is you have it all in one disk space and it's very performance critical. So in Erigon 2, which is the previous version to this, chain data would typically contain pretty much the whole chain. So it could grow on some chains to massively. So, for example, on the Polygon main chain, I think the chain data currently for Erigon 2, the directory size is about 8 or 9 terabytes. And that's a big monolithic file that is essentially hard to operationally manage. Now, the way we've managed that is to gradually move the data from that chain data directory into a set of read-only snapshots. Now, this is because as the blockchain ages, after a certain period of time, basically the data never changes. So what you can do is essentially offload from the MDBX store, which essentially has a read update model to snapshot data, which is basically written once and then it's read only. Now, essentially, the big difference between Erigon 2 and 3 is the difference between the snapshot data and the chain data. So as I mentioned earlier, the chain data for Erigon 2 can grow to up to 8 or 9 terabytes, depending on the chain. The chain data store for Erigon 3 is typically of the order of a maximum of 300 gigabytes. So it's an order of magnitude smaller. And the reason for this is because basically the data that was stored in that database has now been offloaded into a set of read-only snapshots. And I'll explain those snapshots in a little bit more detail in the next slide. So if you go into the snapshot directory, you'll find it essentially has a whole set of files in it, which are essentially the majority these days of the Erigon database. So basically, this is split into two main sets of data. The directories at the top are, which I've labeled state data, are effectively contain the current and historical state of the chain. So basically, this is in Ethereum terms, it's essentially got a monolithic state that is ever updated. The contents of that state and its history are contained in these directories. The next set of local files are split into two, some control files, which I'll not talk through too much in this talk, and a set of things called history files. Those history files contain essentially all the transactions historically that contribute to the state. Now, this is exactly the same data as we've got contained in the chain data store. It's just laid out in a different format, essentially. And the majority of the code in Erigon, which is different from Geth, which we're forked from, is involved with managing the database itself and the snapshot format process. So I think, having explained the way our data's structured, I think there's another thing that's worthwhile understanding, which is how the flags with the Erigon process basically change the way that the data is stored. So we effectively have three modes of operation. and those are archive, full, and minimal. So basically, the default operation of Erigon is to run in archive mode, which basically means we store everything. And what that means is that from the genesis of the blockchain and the beacon chain, everything, transactions, state, beacon chain, and blobs get stored forever on Erigon's in Erigon's data directory. Now, that can obviously get fairly large. I think at the moment a full archive node for Erigon is about for the Ethereum mainnet is about 1.7 terabytes. So it's not as large as the largest chains that we've got, but it's still a considerable amount of disk space, and that's obviously growing. So if you don't want to keep all of that data, you can run with prune mode full, which basically means that the Erigon process, rather than taking data out of its database and putting it into snapshots, takes data out of its database and throws some of it away, essentially. And what that does is just reduces the amount of disk space that you need. Now, basically, full operates with the equivalent data of a get full node, essentially. Now, for Erigon 3, we've also implemented a third mode, which is what we think people will end up running if EIP 4444 gets implemented. So basically what that does is it allows the node to run with the latest state that it needs to operate, but only enough historical data to service that state and manage any finality events. It basically won't service all the standard RPC requests. Now, as I've talked through this, and I mentioned at the beginning, Erigon's normal startup mode is to pull the data that we've got in the snapshot directories from other Erigon nodes to start up with using BitTorrent. And that's because is there for two reasons. One is that the download across the torrent is faster than running the P2P process, but also the data that you download is effectively the compiled form of the chain. So you don't need to rerun the Erigon execution layer in order to get to the state of the chain. Now, basically, this gives us faster startup because we've avoided the whole execution process. Now, if you set the node downloader flag, it does something slightly different. When Erigon starts up, it will start as a plain node and start downloading the data from the dev P2P network and then re-executing it. Now, I'm mentioning that in this presentation because people might want to test the difference between our effectively fast download mode and the no downloader mode, which is kind of like the default operation for the chain. And from a chain security perspective, it's important because basically, as a test of Erigon, you need to basically ensure that it will run with no downloader and execute from Genesis on a chain. And actually, you need to test that the outputs that it produces are the same as you would get if you were to run the download process, essentially. So I'm mentioning that in terms of this because the relationship between the optimization we've got from a download and start perspective to what happens when you start from scratch and download completely is an interesting security policy property of the way that Erigon actually operates. And I think that's the end of this slide. So what I'm going to do is reshare my screen now and walk you through the code. And I'll basically reference what I've talked about here when I'm talking through the code. Right. Okay, so what I'm going to talk through now is the Erigon repo. And so if you look at the, I'll just make this a bit larger. So essentially, so Erigon is structured as a monorepo, effectively. So if you go to the Erigon site and clone it, you'll basically end up with a directory with this set of directories in it, which is effectively the whole Erigon code base. I think to start with at the tree level, I'll highlight some important directories that you might want to look at first. I think the first thing I'll say is if you look at this directory structure and the Geth directory structure, you'll see quite a lot of similarity because Erigon was originally a Geth fork. I would say if you find the directories that have got our original Geth code in it, and there is still quite a lot of that, it should have pretty much the same directory structure. So if you're familiar with Geth and you look at our code base and you see common directories, that's because that's where we started from. Basically, what we've done is we started from Geth and then we've added stuff to it. Now, I think in the state of the Erigon project at the moment, we're just about, as we get to Erigon 3 being released, at the stage where we believe we've finished our initial R&D process. So we're beginning to look at this directory and prune it down to make it more navigable. But I think where we are at the moment is we have basically we've got the union of all code in here. So don't be daunted if you look at it. Hopefully what I'm going to explain now is I'll give you a route through to it so you can find stuff that's relevant to you. I think the first directory to point out is Erigon lib. Now, Erigon lib has got a lot of utility functions that are essentially things that we as an Erigon team have re-implemented ourselves for Geth. Now, I don't think you need to worry about this library when you're initially investigating the code, but it's quite likely as you find yourself debugging or tracing through code, you end up in these directories because this is essentially the core of the Erigon development. So I'm not going to mention any of the details of these this directory. It's just, you know, this is where you can find yourself. Now, in talking through navigating the code base, I think the place to start is essentially here in the CMD directory. Now, if you remember slightly earlier in this conversation, I talked about a set of Erigon components, and their mains all start in this CMD directory. So basically, Erigon here is the starting place for the main Erigon startup, and you'll see, and this is the majority of these things, it's a very simple process that essentially sets up some configuration and runs Erigon, essentially. And what this will end up doing is configuring and creating all the components required for Erigon to run with everything inside it. I'll explain a little bit about that later on, but first off, I'll basically take a look at one of the components I talked earlier, which is the RPC daemon. And again, you'll see this is essentially a main. And what it's doing is setting itself up to execute the RPC daemon. And essentially, the way it does that is by starting an execution context, and then it will start pieces of components from its internal directory. So you can see the, we should find Sentry in here somewhere. The Sentry process starts in exactly the same way. This is actually a simpler process because it's starting up the P2P library. But it's sort of more interesting is you can see its flag uses here. So in terms of code comprehension of Erigon, the place to start is with this commands directory, and you'll see all the various components essentially that you start. The one I think you really care about to start off with is the actual Erigon process itself. Now, the way the things are structured, effectively, the Erigon repo has a main makefile, and you can effectively do make component name, and it should make a running version of the component. And then if you look at the commands here in this makefile, you'll see that the subset of the commands in the command directory that we actually use and deploy. There are a number of other directories there which are of maybe of general interest, but they're effectively there, and we use them for internal debugging processes. So what I'm going to talk through now is essentially the actual startup process for the core Erigon process. And that starts in this, essentially whenever you're running anything in an Erigon process, the standard Erigon, it'll do some command flag configuration, and then it's going to hit this backend process. And what this backend file contains is the startup of all of the various components that make up new. Its new function is a bit of a monolith. It basically goes through and initializes everything and does flags processing. So if you basically want to debug the Erigon startup, this is the place to start from. And effectively, if you look through the code, you'll see it's just going through and setting up all of the pieces of the Erigon execution environment, and then it enters a main loop which loops forever, and that is the Erigon process, essentially. So what is that? In order to understand what that's doing, I'll explain a little bit about how Erigon works as in its loop. So what Erigon has is this thing called stage sync, and if you bear with me, I've just got to find, I think it is stage sync somewhere. Yeah, so if we look at stage sync, what we'll see is a set of stages, and these files that start stage something are effectively Erigon execution components, and they do a number of things in a continuous loop. And what I mean by a continuous loop is if we look at this default stages file, which you'll find if you look back at the back-end code, you'll find that what the back-end code does is sets this and set of stages up and configures it. And basically what a stage is effectively a function that gets called in its forward function, which does a set of processing on the database, And then what Erigon does as an overall process is it runs this master loop, and essentially at the end of every loop it commits the database. Now what this means is that all of the stages operate within the same transactional context. Now the reason we do that is it makes it, if any of the stages crash, we basically can take the whole loop back to zero and run it again. And that's effectively the Erigon processing model, is attempt to run a stage loop. If it fails, try to unwind the process if you can, start again and run the loop. And if you're successful, you just run this loop forever. And I'll just talk a little bit through this process because it explains how it works. Essentially, the snapshot stage here is the process that I explained earlier about taking things out of the database, first downloading them in the first place, and then running them and extracting data out of the database happens at this snapshot stage, which is the first thing that happens. Now, for the majority of the time, the snapshot stage doesn't do anything. The first time you call it, it downloads everything. And then basically periodically, it will copy data out of the database and prune it. And what we mean by prune is delete from the database. You can then think about the processing of the dev P2P network as a process of downloading headers. I'll skip over the next stage, which is only there for polygon processing. But essentially, once the headers are downloaded, we do a process of computing block hashes. So essentially what we've done is we've downloaded the headers, we've computed and stored the hashes associated with those headers. Then we download the bodies, and then we basically compute the senders of those bodies. Now, all of this processing is actually happening interactively with the P2P network. So if you look at the way that the code base is structured, the dev P2P network is continually receiving data, and it's effectively queued until the data is pushed into this header stage. Now, one of the interesting things about that, if you think about the process, it means if this stage isn't running fast enough and the downloader is running, what will happen is the process's memory is going to blow up, because it's effectively keeping all of those instances in memory, waiting for the stage loop to get around and push them into the database. Now, in practice, this is fine from a recovery model point of view, because if the process dies because it runs out of memory, it's just going to restart. It's going to re-download all the data off the P2P network, and effectively it will then try and put it into the database. Now, obviously, if you've got a process that keeps on overflowing its memory, dying and not putting in the database, it's essentially going to be pulling data off the network at an increasing rate, which impacts the performance of other nodes. But essentially, what Erigon does is it does this process in order. And then the key stage it gets to is this stage called execution. Now, what this does, it assumes that all of the headers and bodies and the transactions associated with these bodies are stored in the Erigon database. And then the execution process runs over those transactions and executes and produces state, which effectively it does in a batch mode. So essentially, what you could do, depending on the way this loop is running, you could, for example, download all of the headers from the dev P2P network, then download all of the bodies from the dev P2P network, and then execute everything effectively as three separate processes. So if you think about that in terms of an operating model, if you're operating in that sync mode, effectively you're going to download the 18 or 19 million headers there are in the Ethereum chain, for example, at the moment, store them in the database. Then you're going to download the 18 million bodies, store them in the database, and then you're going to run over and execute them effectively with the execution process. Now, until you finish that, you can't process anything at the head of the chain. But actually, the reason we do this in Erigon is it makes the overall end-to-end synchronization process from zero faster. Now, in practice, actually, that was the Erigon 2 model. In the Erigon 3 model, we've slightly changed it because we've also got a requirement to keep the database smaller. So what we tend to do is run this execution loop in batches of 5,000. So we'll get 5,000 headers, 5,000 bodies, and we'll execute 5,000 bodies worth of transactions. Now, essentially what happens then is there are a series of post stages, of which effectively the only one that we run in Erigon 3 is the creation of the TX lookup index. And what that is used for doing is doing a lookup between transaction and transaction hash. And then you can see with this, finally we finish. So that's effectively the main processing loop for Erigon. So if you want to understand the way the Erigon process works, you effectively look at what's in back end, see how it starts up, look at this execution body code, and what you'll see is it will get continually processed. And if you basically examine what's happening in these pieces of code, you will see the operation of the Erigon execution engine. Okay, so I've talked about the execution engine. What I've missed at this stage is the way that the consensus layer works. So let's look up here at this directory, which is effectively inside of this directory. CL is the consensus layer. So basically, if we're running on Ethereum and we've got an internal CL, as well as the Erigon execution loop that we talked about, we essentially also have another loop running, and it operates in the same way with a set of stages for the consensus layer. So effectively, what you've got is two loops running in the Erigon process. You've got the consensus layer loop, and you've got the execution layer loop, and they interact between them as they're doing execution. So I'm not going to go into a lot of detail with this presentation of the consensus layer code, largely because I don't understand it quite so well, and I think if we want to go into more detail on the consensus layer, we may well be worthwhile organizing a separate session. So that's the main operating pieces of the kind of the core of Erigon. I think the other directories that are of interest if you're trying to look at the way our network interactions work is the P2P directory. Now, if you look at the P2P directory, you'll see pretty much it's a direct copy of the P2P layer in Geth, and we've pretty much as a team done very little to change or maintain it, other than effectively this sentry code. And this sentry code is essentially what operates when you're effectively running the Sentry component. And effectively what this is doing is starting up the P2P layer, the dev P2P layer, connecting to peers and marshalling the processes, the processed packets into the stage loop. So if you want to get an understanding of the dev P2P layer, the place to start is with this Sentry code base. The associated layer for the consensus layer is in this directory called Sentinel. And if you look in the Sentinel directory, you'll see there's a similar process to Sentry, which basically starts up our libp2p connectivity and essentially then directs the data from the network into the consensus layer process loop. And so that's P2P and Sentry P2P. And I think the other directory that it's worth looking into in terms of understanding what's going on is, if you look into, I'm just trying to find it now, because if you look, having said we don't really need to look in Erigon lib, if you look at the downloader directory in Erigon lib, the downloader directory is the driver for our communication with BitTorrent. So essentially, you'll see we've got a wrapper over the top of the standard BitTorrent library that manages the files on our file system and effectively operates a download and an upload process. Now, the thing that I'll say about that with a running Erigon process is, by default, all Erigon processes start up a torrent, and even if they're not downloading, they will operate as a torrent peer uploading. Now, we have a control flag on this to limit the amount of upload that happens, largely because for people who are running with instances that have got egress, which is billed for, they're quite sensitive to the amount of data going in and out of the Erigon process. But in practice, the way our torrent layer works, the torrent cost is relatively insignificant compared to, say, running a TX pool, basically, or even the combination of dev P2P and lib P2P. But effectively, what we've done is we've started the process with this on by default, and the reason for that is we want people to turn it off to make sure we can maintain the health of our current torrent network. In the same way that if you've got any peer-to-peer network, it needs peers, otherwise it gets overly centralized. The other directory that I think is of interest is the RPC daemon code. So if you look in basically this RPC directory, you'll find the root of our RPC daemon service, and essentially you'll see how that gets set up and how that operates. It's effectively a standard HTTP server that's servicing JSON RPC requests. And essentially, most of the operation that it does is to take a RPC request, look up in the Erigon database, and return the results. So in that context, it's a relatively straightforward process. Yeah, and I think that's the end of my overview.
Thank you very much, Mark. Again, we have very much appreciated your detailed walkthrough. So we would like to ask you a few questions that could help our security researchers better understand how to effectively identify vulnerabilities into the protocol. So the first question in the series of 6 questions is, what unexpected bugs have you encountered during past audits, and how did they influence your security assumption or threat model?
So I am not sure we've had, certainly on the current code base, a serious security assessment. So, I mean, I think the interesting thing for us is we're probably going through this for the first time.
Okay, that sounds very, very good. So the next question will be, what key areas should bug hunters focus on and why?
So, I mean, I think we're making a set of assumptions which I think have historically proved correct, in the sense that we're kind of assuming that the core vulnerabilities of our process are essentially handled by the Ethereum Foundation at the protocol level. So essentially, our underlying assumption is, as long as we're following the Ethereum standard operating model, and we're doing that in a technically consistent way, we basically, our vulnerability profile is no better or worse than any other Ethereum client, essentially. Now, I think from a software perspective, that's quite a big, I mean, I think essentially it's a feature of what we are as an Ethereum client, effectively. Now, I think what we're interested in, however, is if you look at what we're doing that's not Ethereum specific, we've got this whole data distribution layer that we've got building on top of BitTorrent. So effectively, I think in terms of looking at Erigon, the question we really want to ask is whether we've actually, what have we done to our security vulnerabilities based on the fact that we've got this parallel distribution layer. Because again, that's effectively reliant on the security model of the underlying the underlying BitTorrent network.
Mm-hmm. Interesting. So, absolutely, yeah.
I mean, I think the stuff that we have dealt with kind of significantly from a vulnerability perspective is we've done a lot of work in our RPC daemon to make sure that we're avoiding denial of service attacks for people who are using us as a provider. And I think that's kind of fairly, again, it's relatively well understood in that we're operating a standard Ethereum protocol and we've got the same threat profile there. But that is also, I think, a point of focus. And then the other thing is there anything we're doing in our application that's different from the other clients? Essentially, we've misinterpreted the various P2P specs in some way, which means that we've got an unexpected vulnerability.
Mm-hmm.
And I think, again, that's probably more significant with it's more significant with Kaplan, I would say, than it is with Erigon's core use of dev P2P, which, as I mentioned in the presentation, is pretty much a we've taken it from Geth and we're operating their model, so we're kind of making the assumption that they've done that security work for us. But again, we may have missed things that they've done, so that opens us up to a vulnerability that we're not particularly aware of.
True. I see. And in fact, the third question is like, are there any specific tips from your team on what to look for in your code base, like ensuring proper use of oracles, or any specific advices or
No, I don't think I have any specific. I mean, because I think a lot of that becomes like application specific. Whereas in fact, actually, if you look at what we've got, it's a fairly vanilla. Well, it's a vanilla Ethereum node. So it's essentially just a network operating component. So in terms of the kind of crypto vulnerabilities, I don't think they necessarily apply to us, but the fact that I said that is sort of interesting, if you understand what I mean, from a vulnerability. It may be the stuff that we should be looking at that we're not, because we think we're out of scope for it.
Right, that's kind of suggested something, just in some way.
Well, I'm just, in the security realm, it pays to be paranoid. That's really what I'm saying.
Yes, so we will rely more on our security researchers' experience at this point.
Yeah.
What resources would you recommend for learning more about your project and code base? Like, is there any documentation or any white paper you would probably point out?
I mean, basically, the documentation on the Erigon website is pretty much the documentation we have, and that's because, as I say, I mean, if you want to know more about what we're doing so effectively, to understand the application phase of what we're doing, the documentation is effectively all there on the Ethereum, the Ethereum Foundation's site, because basically we're taking what they've specified and implementing it. I think what I've tried to do in the walkthrough is give some inkling as to how our underlying data model works, and effectively at the moment that is documented in the code, basically, other than us having third-party documentation or white papers.
Thanks. So another question is, can you explain the different access control roles within your protocol?
So we don't use access control at all, essentially.
Yes.
For the Erigon node, if you've got access to the node, you've got an open network, you can send anything you like to it, basically.
Okay.
Yeah. So
straightforward.
Yeah.
And which areas of your code base are likely to be the most challenging for auditors, and where do you expect bugs to arise due to implementation complexity? But here's more likely the question that we were discussing earlier. There might be some ideas, some suggestions, but we rely on the security researcher experience. But I mean, if you think of any areas to point out, yes.
So the reason I talk through the stage loop is effectively that if you look at the Erigon code base, it looks fairly large in terms of code comprehension. But actually, if what you do is concentrate on what the stage loop processing is doing, everything else runs out of that. So I don't think there's any need to really understand from a security perspective what we do to manipulate and store data, which is the majority of our code base. And some of that is convoluted, to say the least,
Mhm.
basically. So I think the advice I'd have is, you're beginning to get that into that bit of the code. I don't think, from the point of view of doing security research, you need to understand it, because essentially at a risk level, it's formatting data and sticking it on a disk, if you see what I mean. So it's entirely internal. I think the place that the security vulnerabilities exist are at the network interface, basically.
Absolutely. Right, Mark, we covered essentially the 6 questions that we wanted to make on top of your detailed technical walkthrough. So thank you so much. We thank you everyone who joined the call. This has been a very productive section. So I'm sure there will be any follow-up questions as our security researchers start studying your code base. So please let us know, and Mark will be happy to provide any clarification if need be.
Yeah, and I'm certainly kind of expecting there may be a set of questions which I'm happy to answer.
Perfect. Thank you so much.
Okay.